So the first problem is, what is the self-inductance of a coil whose reactance is 10 ohms at 60 hertz? Okay. So XL is omega L, and which is 2 pi FL, and they tell you this XL is 10 ohms. Okay. L is 10 ohms. 60 hertz is 1/seconds. Okay. So ohm times second is what? Henry. Very good. Okay. So 26.5 millihenry. Okay. At what frequency is the reactance of a 20 microfarad capacitor equal to that of a 10 millihenry inductor? Okay, so you want XL to be equal to XC. And this is the frequency at which it happens. Okay. And omega is 2 pi F. All right, so this is 10 minus 2, 10 minus 8, 10 minus 4, and that will come up. So this is equal to 10 to the power 4, 2 pi, square root of 20 hertz. Okay, so at that frequency, XL will be equal to XC. So you guys understand, XL is omega L and XC is 1/omega C. So if you plotted XL and XC as a function of omega, that linearly increases, and that, okay. So only at one frequency will they equal each other, okay? In an RLC series circuit, the voltage amplitude and frequency of the source are, so the voltage amplitude is 100 volts and 500 hertz. R is that, L is that, C is that. What is the impedance of the circuit? Okay, so when you get this kind of problems, what you want to do is calculate XL independently. And all impedances are in ohms. And notice something. See, for all these things, you'll generally be operating at frequencies where the impedances are comparable. At least in the problems, you'll see this. So this is 500 ohms, this is 628 ohms. I guess all the impedances will be similar. XC is 1 over omega C equal to 500 times 2 is 1,000. That makes it 10 minus 3. So this is 10 to the 3 divided by 2 pi. And again, ohms. Okay. So again, see, they're all of the same order. 500 ohms, 159 ohms, and 628 ohms. So there's XC, there's XL, and so Z is R square plus so the impedance of the circuit. And by the way, so this is a series RLC circuit. This formula works for a series combination. Okay, won't work for a parallel combination. What is the amplitude of the current from the source? The amplitude of the current I max is V max over Z. V max was 100 ohms, 100 volts, and Z is 686 ohms. the amplitude of the current is 0.15 amps. Okay. If the EMF of the source is given by that, how does the current vary with time? So essentially what they're asking you is, they're asking you for phi. Okay. So phi is tan inverse XL minus XC divided by R. Okay, so IT is, the amplitude of the current is 1.15 amps sine omega t minus 0.75. There's phi. Okay. And by the way, so we know omega sine, what was the frequency? 500 hertz. All right, so there is I as a function of t. Okay. Does this guy cook anything? Yes. So there's the voltage. It's a series RLC circuit. What are the total impedance? So same thing, we'll do the same thing. 2 pi, so it's a 60 hertz. F is 60 hertz, you can see that. Okay, so R is 5 ohms. XL is omega L, which is 120 pi. Omega is 120 pi. Radians per second. Okay, so as mentioned, see all the, you all, in general in these problems, you're operating at a frequency where all these impedances are comparable. 5 ohms, 9.4 ohms, and 6.6 ohms. Okay. The total impedance So the total impedance of the circuit at this frequency is 5.7 hertz. What is the phase angle? The phase angle is tan inverse of XL minus XC over R. That is 9.4 minus that, that's 2.8 divided by 5. .2 degrees, and write an expression for I. Z is 5.7 ohms, so there's the amplitude of the current. Okay. Again, you're finding Z's and P's. The EMF of an AC source is given by that, where V naught is 100 volts and omega is 200 pi radians per second. Calculate the average power output of the source if it's connected across a 20 microfarad capacitor, a 20 millihenry capacitor, and a 50 ohm resistor. When you, okay, so the average power output is, the expression is V RMS IRMS. Okay, so this is the expression for a DC circuit, V times I, the average power output. Since this is an AC source, you get multiplied by the power factor. For a purely capacitive and an inductive circuit, what is phi? For this guy, it's minus pi by 2. For this guy, it's plus pi by 2. So this would be 0. So the power output for A is 0. For B is 0 as well. And for C, for the resistor, for A, P is minus pi by 2. VRMS is 100 volts. And IRMS is Imax. Imax, which is Vmax over R. So the average power is Vmax square over R times 2. So the average power delivered is 100 watts when it's connected to that pure resistance. Okay. Okay. An AC source of voltage 10 volt delivers electrical energy at a rate of 0.8 watts when its current output is 2.5 amps. What is the phase angle between the EMF and the current? Okay, so they don't, a voltage amplitude is that, and the current, so we're assuming this is the current amplitude. Okay, so average power is VRMS IRMS times cosine phi. Cosine phi is and this is equal to P average Vmax Imax divided by 2, so you get that over 2. Yeah. And okay, so we have 2 times average power is 0.8 watts, voltage amplitude is 10 volts, and current amplitude is 2.5 amps. So cosine phi equal to 1.6 divided by 25. Well, I'll leave it and, okay. Okay, is this guy cooking? Hmm?
Yeah, but pretty bad.
Barely, yeah, okay, so you're close to 90 degrees. The resonant frequency of an RLC circuit is 2000 hertz. If the self-inductance in the circuit is 5 millihenry, what is the capacitance in the circuit? Okay, so the resonant frequency is equal to 1 over LC. Yeah. So omega square so the capacitance is 1 over 4 pi square F square L. Okay, that's 10 minus 3, so this is 10 to the 6, so, and then you get 10 minus 3 on top. So 10 minus 3, this will work out in farads, 4 pi square into 4 into 5. Okay. 1.27 microfarad. This problem says, what is the resonant frequency of a resistor, capacitor, and inductor connected in series? R is that, L is that, and C is that. So resonant frequency has nothing to do with the resistance. Okay, so the resonant frequency is L is 2 henries, C is 5 microfarads. Okay, square root of this is 10 to the minus 3, and that comes to the top. So the frequency is hertz. this is 50 hertz. Okay? This is the frequency that they use in Europe. If this combination, okay, so that's part A. If this combination is connected to a 100-volt source operating at the resonance frequency, what is the power output of the source? Yeah. At resonant frequency, what is phi? 0. What is Z?
Just resistance.
Just R. Okay. So R squared plus XL minus XC square. At resonant frequency, this is 0, so it's just R. So at resonance, IRMS is VRMS over Z. And Z is equal to R, so. And what is the voltage amplitude? 100-volt source. So this is a 100-watt device. What is the Q of the circuit? The quality factor of the circuit. What does Q tell you? It's the average power delivered as a function of frequency. Okay, tells you how sharp the peak is. Okay, so you're delivering maximum power at resonant frequency, and you come off that frequency. What you generally want is the power to fall off drastically. Okay, so this device would respond well to the, is responding to the natural frequency. What is the quality of the factor of the circuit? Q is and quality factor is omega naught L over R. And okay, so the resonant frequency was that. So essentially 4 pi. We'll just set 12.5. It's a little, and this is a dimensionless quantity. Okay. Omega naught frequency divided by frequency. what is the bandwidth of the circuit. The bandwidth is, this is the bandwidth. Okay. So the bandwidth is quality factor. Bandwidth is omega naught divided by quality factor. Okay, the reason I calculated it this way is, okay, so the peak frequency is, in terms of frequency, this is 50 hertz, and bandwidth is 4 hertz. So at 52 hertz, the power is half, and 48 hertz, the power is half. Okay, so bandwidth was 4 hertz, so either side less than 5%. Okay. The bandwidth is 10% essentially. A step-up transformer is designed so that the output of its secondary winding is 2000 volts when the primary winding is connected to 110 volts. Yeah. If there are 100 turns in the primary winding, how many turns are there in the secondary winding? So this is a step-up transformer. V2 equal to N2 over N1 V1. And again, you put RMS value, you get RMS value. You put maximum value, you get maximum value, and so on. You know. So you want the windings in the secondary N1 V2 over V1. You have 100 turns. V2 is 2000 volts. 110 volts. So 1800 turns in the secondary. Okay. So this transformer is stepping up the voltage from 110 volts to 2000 volts. If a resistor connected across the secondary windings draws an RMS current of 0.75 amps, what is the current in the primary winding? Okay, so again, no free lunch. Input power is equal to output power. Okay. So input power is VRMS, IRMS, input equal to VRMS, IRMS, output. Okay. What is the current in the primary winding? I RMS input equal to VRMS. So the input current was that. Okay, so you see the current falls down. Input current was this, theirs was the output current, and the output voltage is up. Okay. Okay, a transformer is used to supply a 12-volt model train with power from a 110 volt plug. So this is RMS value, and we'll assume that's RMS value. The train operates at 50 watts. What is the RMS current in the secondary coil of the transformer? Okay, so power output is VRMS, IRMS. Okay, so 12 volt times, so 50 watts. What is the RMS current in the primary coil? Output power was 50 watts. RMS input is 110 volts. What is the ratio number of primary to secondary turns? V2 over V1 is N2 over N1. So N2 over N1 is V2 was 12 volts and V1 was 110 volts. Point 1. Okay, so 10 to 1 windings. What is the resistance of the train? D. Okay, so power output is V RMS square divided by resistance. 12 volts square. Okay. What is the resistance seen by the 110 volt source? So the input resistance is 110 volts square divided by 50 watts. Okay, the same formula except on the input side. Input voltage was that, and input power is also 50 watts. Okay. 242 ohms. All right, guys, so